So thank you for the invitation and being able to speak here. So what I want to talk about today is sort of in the spirit of the day is about networks, right? And in particular, when we collect large-scale network data, we figure out that this network exhibit lots of very interesting patterns and sort of structures in them, right? And one of the most sort of prevalent structures or things that we go after is this emergence of clusters, right? So these real-world networks, they're not sort of uniform or homogeneously connected, but they exhibit some kind of notion of clusters, right? There are regions in the network where the network is more densely connected, and there are regions where the network is not so densely connected, right? And here I'm just giving you one picture. This is from, this is the blogosphere. Adámics and Adaris, the paper, was analyzing sort of Republican versus liberal blogs, and they found out this separation and formation of these two clusters, right? And the question is, for example, why do these clusters form in these networks, and what do they correspond to? And really, if you sort of go back to the literature, first thing that I'd like to do is sort of make this distinction for the purpose of this talk between clusters and communities. And what I will use the word cluster for is just sort of a set of nodes that has a particular connectivity structure. So what do I mean by that is, for example, an intuitive definition of a cluster is a set of nodes where there are many connections between the members of the set. So that would be one possible connection. The other possible connection of a cluster could be all the nodes that have degree 3, for example, right? And then there is this other thing that is what we call network communities, right? And really, this is a set of nodes that has some kind of latent or shared property together, right? And really, the assumption that you are making is that you will be able to discover these communities given the network structure alone, right? So if you imagine a social network, you go in there with a hypothesis that there are these dense clusters form in the network. So if you have some algorithm that will identify these densely connected sets of nodes, these sets of nodes will at the end correspond to these real social communities. Maybe people that are in the same department at the university, or that were born in the same town, went into the same high school or something, right? But at the end, you hope that this cluster, you will be able to interpret it and find something that these nodes have, sort of some latent property that is common to the nodes, and sort of explains why they are linked in that particular way, right? And clusters don't only form in social networks, but also sort of you can find them in the web graph, where sort of topically connected web pages tend to link to each other more. In citation networks, right, you would imagine that clusters correspond to different disciplines, areas of research, and so on, right? And really, if you ask why do communities form, right? So for example, one of the bases why communities form in social networks is basically goes back to the work of Mark Granovetter and his work on the strength of weak ties, where he sort of talks about these strong ties that are well embedded in the network, sort of that strong ties are between the nodes that share many friends in common, and then there are these kind of long-range weak ties in the network, right? And you can use this intuition to start formalizing algorithms that would go sort of hunt for these clusters or communities, right? And if you look at the algorithms that are based on graph partitioning, or algorithms that are based on modularity optimization or between centrality work by Mark Newman, right? Those methods are basically going after identifying these weak edges, these sort of long-range edges that span these clusters, and the idea is that you can sort of cut or remove these weak connections and whatever is left, this will be sort of dense clusters, and then you take those and try to interpret them as sort of real communities, right? So that is one way how to go about community detection in networks. Another thing that sort of people soon realized after that is that here the picture on the left is sort of a prototypical picture of how networks would look, or the cluster structure of networks would look under this strength of weak ties hypothesis or theory, right? But then you can also say that nodes in networks belong to multiple clusters, especially in social networks, you can say. So the other realization then is to say, okay, communities in networks overlap, right? So a node can be a member of many communities. And you could think of yourself as here, and these are your work friends, and these are your family friends, or something like that, right? And how do algorithms that do this, how do they work, right? The way The way these algorithms work is basically they assume that the picture that I showed you on the previous slide, right? That there is this node in the network that is sort of a member of different social circles. And one way how to go detect overlapping communities is, for example, through this Clique percolation method. Right, so we want to detect overlapping communities in networks. How do we go to do this? One possible method to do this is through this method called Clique percolation, and the idea is to identify clique graphs and then see how these sort of maximal cliques, how they overlaps, right? So the idea is the following. First, I will define this concept of a k-clique, which is just a fully connected subgraph on k nodes, right? So a clique on 3 nodes is a triangle, right? Then I will define the second concept where I say what does it mean for 2 cliques to be adjacent. And I will say that 2 cliques are adjacent if they share k-1 nodes. Right? So for example, 2 triangles up there, that's an example of adjacent k cliques where k equals 3. Right? So 2 triangles are adjacent if they share 2 nodes or if they share an edge. Right? Two 4 cliques would be adjacent if they would overlap at the 3 nodes. Right? And so how does the method now work? The method works the following, by basically saying that communities in networks are composed of these overlapping k cliques. So the idea is the following, right? So if I give you a graph, what you will do is first you have to decide on what is your parameter k. In our case, let's imagine this parameter k equals 3. So what I will do is first I will go and identify maximal cliques in the network, right? So here's the first clique, here's the second clique, the third one, and the fourth one. And what I will now do is I will create this sort of surrogate graph where nodes will now be represented as cliques, and I will connect 2 cliques if they are adjacent, right? So my 4 clique and the 4 clique called B and 4 clique called C are adjacent because they share that edge together, so I connect them, right? And now the connected components in this clique graph will form communities, right? So if I go back to my red graph, this would mean that I found this community and I found that other one, right? And that red node in the intersection is member of both communities. It's a member of community A and this BCD community, right? So this is sort of what is how community detection is done today, and you can sort of generalize this and make things probabilistic and smooth, and sort of you arrive to models like mixed membership stochastic block model, where the idea is now that you have a probability distribution over your community memberships, and then for every pair of communities, you know what is the background linking probability for that pair of communities, right? So that's the second part of things, right? And really, now I want to start telling you about our work that my student Jaewon Young is doing, right? And really, if you go and think, how are we going about discovering clusters or communities in networks, right? We go and we take some data set. Maybe we take the DBLP, who writes papers with whom, who collaborates with whom data. Then we represent this data as a graph, as a network, as an interaction network. Then we go and run our favorite clustering community detection algorithm on the network, and then we go and try to interpret the clusters, right? And really, the problem is in this fourth step, where you sort of have to go and manually examine and try to argue that your method makes sense, right? And in this particular case, if I work with DBLP network, right, then I could go and argue. This is terrible. I could go and argue that my communities correspond, for example, to people that work in the same area or to people that publish in the same journals and so on, right? So what we did in our work is we said, okay, are there networks where I would have some good or somewhat reliable notion of these ground truth communities, right? So what I would like to do is have networks where I find labels for these clusters ahead of time. And that would help me quite a lot, and I'll tell you how that would help me. But first, are there such networks around? And actually there are, right? So in this particular DBLP case, a valid proxy for this sort of true latent clusters would be just labels of which journals and scientific conferences people published at, right? So that would be one possible way, right? In social networks like LiveJournal, Facebook, and so on, people explicitly create groups that other people then join to, right? So again, you have some kind of notion of ground truth clusters or communities that you would like to detect, right? In information networks, people create sort of topic-based groups of the nodes in the network. And just to give you an idea how this, for example, in social networks, how these explicit groups form is here's the data for the LiveJournal network, which is a social network of bloggers, and people create groups that then others join to, right? And these groups are created around, basically the LiveJournal classifies them into culture, entertainment, expression, freedom, gaming, sports, student life, and technology, right? Or for example, another case is there is this social network on patients with diabetes. And if you look at what kind of explicit groups are created in this network and how these groups are named, they actually exactly correspond to what you would hope to find sort of the structure of that network to correspond to, right? So you have people that groups on people on patients of about the same age. You have groups on emotional and social support, different geographical regions, people with different types of diabetes, and so on, right? So really, what I want to say is that these groups correspond to something real, to something that you would hope to discover from the network, right? So here is a set of networks where we were able to find some notion of this kind of ground truth clusters, right? I have 5 different social networks, a collaboration network of DBLP, and then a product co-purchasing graph of Amazon. These networks have between 300,000 and 100 million nodes, between 1 million and 2.5 billion edges. The number of communities is between a few thousand up to 8 million. And then an average size also varies quite a lot, and A is the average number of memberships. So basically, how many communities a node is a member of. And in some, nodes are members of many communities, and in some, most nodes do not explicitly define memberships to any of them. And really, what do I have now is I have this kind of labeled graph where every node tells me what clusters the node is part of, right? And what this allows me to do is basically it allows me to run now community detection algorithms and evaluate, measure how well are they performing, right? So there are sort of two consequences of this. First consequence is that I can now ask just empirically, how do groups, these ground truth communities, how do they map on the underlying network, right? And this way, maybe I can design better algorithms or models for network communities. So if I have this notion of ground truth communities, what can I do? There are 2 things I can do. First thing is actually I can go and examine how do these communities overlap, and maybe I can go and design better algorithms. And then the second thing I can go and do is actually now go and evaluate them, right? I can compute some kind of notion of accuracy. How well do these community detection algorithms, how realistic clusters do they detect, right? How well do those clusters correspond to my ground truth labels? Right? And here is the first basic thing that we did, right? Was just asking what is the probability that a pair of nodes is connected given how many groups they share in common, right? So sort of for every pair of nodes, I ask how many groups do you share in common and what is your probability of linking, right? And what you see, maybe not so surprisingly, is that the more groups you have in common with another person, the more likely you are to link. What you also see is that the probability of an edge, as soon as you share a few communities, basically goes closely up to 1, right? And the background probability of having an edge in these networks is like 10 to the minus 5, 10 to the minus 6, right? So as soon as you have 2 or 3 communities in common, this jumps up for basically several orders of magnitudes up to 0.1, 0.2, all the way up to 1 after you are further out there, right? So kind of this is very intuitive observation. But if you ask, what does this really mean, right? What this really means is that the parts where communities overlap, right? Sort of the parts where there are multiple clusters overlapping have more edges than the non-overlapping parts of the network, right? And if I give you this picture in a different view, here is a different view, just pictorially what's going on, right? So what I'm showing you here is 3 different ways of how you could go think about network community structure, right? So this is what you could think about if you have this kind of densely connected clusters that are connected by a few edges, right? So then this is sort of pictorially how you can think of the network, and if you think of the adjacency matrix, then you can think of it like this, right? You have this dense cluster, and these are sort of the edges that connect the 2 clusters. If you think about what the mixed membership stochastic block models or the the Clique percolation method is saying how clusters overlap. It's really telling you that, or the assumption they are implicitly making is that the clusters overlap in this way, right? Sort of that here where the two clusters overlap, the probability of a connection is smaller than in the non-overlapping parts of the cluster, right? And what the graph on the previous slide shows you is that the way clusters really overlap is something like this, right? Sort of that these red nodes, because they share two cluster memberships together, not just one, are more likely to be connected than these nodes on these sides who just have one membership in common, right? So really what this is saying is that the parts of the network where communities overlap are more densely connected. And right, if the reality is not like this, but is like that, then you can ask, does this matter at all? And can I go and now design a clustering method that will identify clusters while sort of allowing for this kind of overlaps between clusters? And just to quickly show you that sort of present community detection methods, at least the ones we know and we were able to find, don't do this. Is, for example, if you think about the Clique overlaps, right? As soon as you will be adding edges between these nodes here in the middle, these cliques that otherwise wouldn't be overlapping will start to overlap. So you will either confuse this as one big cluster, or you will confuse the overlap of two clusters as a cluster of its own. And what will happen in mixed membership stochastic block model is that, again, you will sort of confuse the overlap of two clusters as a separate cluster. So now the question is, can we come up with a method that will be able to identify these densely overlapping communities or clusters, right? And here's a way how you can go think about this. And here is where the affiliation graphs or this kind of bipartite models of network structure come to play. So here's a generative model of networks that is very similar to what to the affiliation network model of Latanzi and Siva Kumar, but is a bit sort of different in a very small but very important detail, right? So the way the model looks like is the following. You have the nodes of the network, and you have the nodes on the top are your communities, right? And the node of the network links to the community they are a member of, right? So this means that green nodes are just members of community A, while these red nodes are members both of cluster or community B and of cluster A, right? And then what I will also do is, to every community node, I will assign a single parameter, a single probability. And all I will do is to say that members of a single community link independently with this small probability, right? And then nodes that are members of two communities, they get two coin flips, right? So the probability of an edge between this pair of nodes, they will be connected either if this coin comes up heads or that coin comes up heads, right? So naturally, the more communities you have in common, the higher probability that at least one of these coin flips will come up heads, so the more likely you will be connected, right? So this kind of very simple model already gives you this property that clusters, sort of the overlap of clusters tends to be more densely connected than the non-overlapping parts, right? So if this is my model, then the next question is, how expressive is this model? What kind of structures can it express, right? And what is nice about it, that you can actually model many different network structures, right? So if you want to have communities that don't overlap, then you can model this with an affiliation network like this, right? I have orange nodes belonging to the orange community and blue nodes belonging to the blue community, but there is no overlap between them, right? If I want to have hierarchically nested communities, I can super nicely represent this with this affiliation network. I have this mother community B that everyone is a member of, and then I have subcommunities A and C, and some nodes are members of A, and some nodes are also members of C. And right, if I want to have this kind of two communities that have some overlap, again, I can easily represent this with this affiliation network, right? So if I have this model that we developed, I can nicely model the structure of the network and the membership, explicit membership of nodes to multiple clusters, right? So what I showed you now is, if you give me a model, how I generate a network, right? And really, what this model is saying is that each of these communities basically generates a small Erdos-Renyi subgraph, and then I'm modeling the network as a set of overlapping Erdos-Renyi graphs, right? So sort of that's another view of what we are really doing. So I told you how to get from the model to the graph. So now I can sort of try to reverse the whole thing. I say, you give me the unlabeled graph. What is the most likely, or what is the best affiliation network model that would generate the edges as I see them in the graph, right? So what I want to do is, given an unlabeled graph on the right, I want to find the model on the left. Right? And what do I mean find the model? I want to find the affiliation graph, right? I want to decide how many communities I have up here. So what do I want to find, right? I want to find the affiliations, I want to find the number of communities, the number of square nodes, and I want to find these parameters that tell me what is the probability of members of a single community to link with each other, right? And the idea is that yes, we can find, basically you can develop a parameter fitting method that given a graph will identify the clusters. And the way you can do this is basically you can formulate the whole thing as a maximum likelihood estimation problem, right? So basically you say, I want to find the model that is most likely to generate my graph. And the likelihood has a very natural form, right? You just say, I go over all the edges of my given graph. This is the probability that that edge appeared in the graph. And then I go over all the edges that did not appear in my data graph. And this is the probability of those edges not appearing under my model. So what I want to do now is, find this guy B, on which these probabilities depend on, such that this likelihood is maximized, right? And the way we do this is basically we apply a coordinate ascent type of procedure, right? So searching over the bipartite graph is clearly intractable. So what we do is basically we are using some kind of sampling or MCMC-like technique to randomly make small perturbations to the graph and see what does that do to the likelihood. The other thing that is nice, if B is fixed, then you can show that finding the optimal parameters P sub C is convex. So you can just use some gradient method and solve that. And at least our experiments on synthetic data show that the method works relatively well. You try a few random starting points, run this kind of two-step procedure a few times, and you will converge to a good part of the space. Right? So now, if I'm given a graph, right, and I find my bipartite affiliation network, what I really did is I discovered communities, right? For every node in my graph, I know what the community memberships are. So what I can do now is start asking, okay, how well does this method work, right? So, and I can, the way to quantify this is to say, how well do my discovered communities correspond to the ground truth communities? And there are many different scoring metrics that I can use to do this, right? I can use the F1 score. I can use what is called the omega index, which for every pair of neighboring nodes asks how many communities do they have in common in the true network and in under your detected communities. You can use the mutual information between the detected and the ground truth communities and so on. And then for comparison, for the results, I'll show you the comparison with the mixed membership stochastic block model, and then sort of two other methods. One is called link clustering, and the other one is called Clique percolation. And to show you the results, the way, here is what we do. We have these three different scores that I said, and what we do is we sort of normalize them so that the maximum is 1, and then we stack them together and sort of come up with this kind of composite score of each of the 4 algorithms. And what is here to say is that we outperform the link clustering and Clique percolation method for like 60 to 50%, and mixed membership stochastic block model for 10% over the whole networks, and then for about 26% absolute in terms of just over the overlaps. And we also did more experiments with basically with networks where you have node metadata, and then you ask when you detect communities, how accurately or how clean are is the metadata of those nodes. And this was the evaluation that was used by An and others in their Nature 2010 paper. And there we find similar levels of improvement. So the thing that I would like to end this talk with is actually a connection to our previous work, right? So the first thing I want sort of you to take out of this talk is, first is the empirical observation that is like super intuitive, but somehow has been ignored by the community detection algorithms is that the places where communities overlap, you have more connections than in the non-overlapping parts of communities. And then the other thing is this community affiliation graph model, as we call it, that allows you to detect communities with such overlaps. And this sort of beats the state of the art on our data and on our ground truth communities, as well as of using other people's data and other people's evaluation strategies, which was the second experiment I talked. But really what I also want to make a connection to is this work that we published a few years ago when we were arguing that in large networks there are no communities, right? And now I talk to you about communities. So here I'll tell you why that thing is still true and this thing just sort of makes it more true. Right? And what we did in that work, we were arguing that the structure of large-scale networks is more something like this, right? That networks have this kind of small little clusters on the edge, and then you